Yeah. So in this case, the last calculation that I presented to you was the final step of the, let's say, application of the second quantization formalism to the case of the electron-electron interaction. So what I would like to do now is just to make a short summary of the, let's say, topic electron-electron interaction, and then to start with the introduction of a new topic after that. So in this case, in this part of the lessons, I presented you what happens if we consider the effects of the electron-electron interaction. And yeah, so in this case, what we do is to remove the independent electron approximation. So in this case, we let the negative charges of the electron to fill the presence of all the other charges that we have in the system. In principle, we saw that this should correspond to the introduction of a wave function that is a wave function that depends on the variables, both position and spin of all the electrons that we have in the system. But from the mathematical point of view, this is a task that is nearly impossible to fulfill, because we have a wave function that should depend on a number of coordinates that is of the order of 10 to the 28. So all the procedures try to, let's say, find an expression for the wave function of the system using single electron levels. So in this case, we have the Hartree approach and the Hartree-Fock approach. In both cases, the final expression for the wave function is introduced through a, let's say, product between single electron wave functions. The main difference, and yeah, one step back. If you want to make a simplification over the structure of the wave function, you have to introduce a simplification also over the Hamiltonian, because in general, the Hamiltonian includes one-body operators, the kinetic one, and the interaction with the lattice are one-body operators, and the electron-electron interaction is a two-body one. In the case of the Hartree approach, the idea is to remove the two-body operator from the Hamiltonian by replacing that with an operator where you have an interaction between one electron and the average density charge of all the other electrons. So in this way, the Hamiltonian is written in terms of just one-body operators. And due to that, the final wave function that is introduced with the Hartree-Fock approach is just the product of single electron wave functions. So this goes through, again, also a modification of the Hamiltonian. In the case of the Hartree-Fock approach, the Hamiltonian is kept. You keep the two-body operator in the Hamiltonian, but you remember the fact that the electrons are fermions. So if you exchange two fermions within the electronic wave function, then in principle, you should have a change of the sign of the wave function. So to fix this symmetry, we have the introduction of this later determinant, and this later determinant has the same structure of the Hartree wave function, but in this case, you include all possible permutations of the indexes of the levels with respect to the index of the electron. So in this situation, you have a new expression for the wave function, and that includes the antisymmetry of the system. And in this case, you have the opportunity to apply the, let's say, if you apply the Hamiltonian to this wave function to find the to find the expectation value of the energy, what we find is that we have, for what concerns the, let's say, the interaction energy due to the electron-electron interaction, we have two terms. One term is the typical one that you expect to have between the, let's say, that is due again to the interaction between 2 point charges that interact with each other. But the new one is the exchange contribution, and the exchange term is a direct consequence of the antisymmetry of the global wave function. So this is the pure, let's say, as I told you during the lesson, this is again a term that is quantum mechanical because you have no classical equivalent of that. And this depends on the fact that we have chosen a wave function that respects the antisymmetry that we expect for fermions. So the exchange term is due again to the symmetry properties of the electronic wave function of the system. So one side of the electron-electron interaction is a modification of the equations, in particular of the Hamiltonian and of the global wave function of the system, to consider the fact that now the electrons feel the effect of all the other electrons. But another side of the electron-electron interaction is the screening effect, where screening means the fact that if you have one electron in the system, the trajectory of that electron within the system is not the trajectory that you would have had only thanks to the contribution of the lattice, but is a trajectory that accounts both, that depends both on the contribution of the lattice and the contribution of all the other electrons, because now the electronic charges may change their distribution due to the fact that they feel that they are surrounded by other negative charges. And this effect induces a variation of some properties of the electrons, in particular of the relative permittivity. So what we saw is that the relative permittivity in the case of electrons is 1 plus k0 squared divided by q squared. And thanks to this new expression for the permittivity, we have that the interaction potential between the electrons is not the pure Coulombian one as we would have in empty space, but is the Yukawa. And in the Yukawa case, we have a dependence that is proportional to 1 divided by r, as we have in the Coulomb potential, but we also have an exponential cutoff. And the exponential cutoff means that the distance over which the interaction is strong is not infinite as for the pure Coulombian potential, but is just over a distance that is of the order of 3 times 1 divided by k0. K0 is of the order of kf, so 1 divided by k0 is of the order of the lattice spacing. So this means that the redistribution of the electronic charges in the system, thanks to this screening effect, is so important that the screening contribution is able to, let's say, strongly decrease the contribution of the electron-electron interaction even over a small distance, because at that point, 2 electrons whose relative distance is of the order of 10 nanometers, let's say, do not feel the presence of the other one. So in this case, if the distance between the charges in the system is larger than, again, some lattice spacings, at that point you may consider that those charges are not feeling the effect of, that each of those charges do not feel the effect of the other charge. So this is quite important in depressing the contribution of the interaction potential, and is also important as a side effect to justify the initial assumption that we made before discussing the solid state properties, that is that we may neglect the contribution of the surface, because the surface is a sort of, say not a sort of, but is a strong modification with respect to the solid state potential. But due to this strong reduction of the effect of a modification, let's say, of the potential that the electrons feel in the system, the effect of a surface is limited to, let's say, a few nanometers close to consider a bulk solid, then we may suppose that the bulk solid is infinite from the point of view of the discussion of the properties, because the electrons that are within the solid do not feel the effect of the external surface of the solid itself. Due to that, we observed that the expectation value of the exchange term is not as strong as we would expect for the pure Colombian potential, but the modification induced by the exchange term is small. And in particular, what I told you is that the Fermi velocity, even in presence of the exchange term, is nearly equal to the Fermi velocity in case we consider independent electrons. So this means that at the end of the story, even if we consider the electron-electron interaction, direct term, exchange term, the effect of that over the electronic energies is negligible. And in particular, the effect of that over the Fermi velocity, that is an important parameter when you discuss the electronic properties, is very, very small. So at the end of the story, even if we consider the electron-electron interaction in a system where we have a huge number of particles, so where you should expect a strong contribution of the interaction, then at the end, this strong contribution is not observed. And the motivations behind that are, on one side, the effectivity, the effect of the screening contribution, because you strongly depress the long-range tail of the interaction potential. And then another term that prevents a strong contribution from the interaction is the Pauli exclusion principle, because as we saw for levels close to the Fermi energy, the fact that you may have occupied levels in the system prevents some scattering processes to be observed. So the exclusion principle is a strong constraint concerning the electron-electron interaction. Indeed, as we saw before, to require the stability of the Fermi sphere, we have to apply a strong constraint concerning the initial and the final levels in the system. So the initial levels have to be found in the system, but the final levels has to be exactly equal to the initial ones. Because otherwise, if you start to populate levels out of the sphere, at the end you destroy the sphere itself. And as we see that the actual systems are stable over time, then we have to suppose that the electron-electron interaction preserves the Fermi surface, or in general, the electronic structure that we may evaluate in the system. So all those contributions here give a strong contribution to the depression of the contribution of the interaction between the electrons. And one last point I would like to stress is the fact that in this discussion, we always, let's say, the effect of the interaction is described in terms of single electron levels and a modification of the energy. So even if in principle we should consider a wave function that depends on the coordinates of all the electrons, so in principle single electron levels should not be there. Single electron levels are considered, and the effect of the interaction is shown just by the energy of those levels. So the electronic levels are always single electron levels, and the only contribute on the interaction affects the energy. We saw that this may be fine due to the fact that the relaxation time due to the interaction is very large with respect to the relaxation time due to collisions. So in this case, from in between collisions, the effect of the interaction between the electrons can be neglected. So only if we were able to have a system where the relaxation time due to the collisions is 4, 5, 6 orders of magnitude larger than the one that we have in actual system, then maybe we should be able to find some effects of the interaction. But in general, this is not the case. So at this point, we may just, let's say, consider the effect of the interaction just as an effect that influences the value of the energy. And I include here an additional comment that I didn't present to you before because I just wanted to keep this part small. And the comment is the following. If we supposed to be in a pure free electron, sorry, if we supposed to be in an independent electron picture, then we have the opportunity to find all the possible levels that we have in the system, as we did for the Sommerfeld model, for the block model. So in both cases, we may define a set of levels that the electrons should occupy when we include those electrons in the system. When we consider the interaction in between the electrons, what we are saying is that we still have the opportunity to define single electron levels. Here I just write K prime to say that these are the indexes that distinguish the single electron level in case we have independent electrons. And these are the wave vectors that describe the single electron levels when we consider the effect of the interaction. So the idea is the following. This single electron level that we have in case we consider the interaction is an electron level that corresponds to what? That corresponds to one electron that is interacting with all the other electrons. So from the point of view of the comparison with the previous picture, we have a sort of ideal gas. So the electrons are independent and the electrons do not interact with each other. So just if you had an ideal gas. In the second case, the ideal gas approximation disappears because one electron feels the effect of the other electrons in a not so strong way. So this K prime one here represents one electron together with the interaction between that electron and all the other electrons. And in general, this system here is described as a liquid because in a liquid, you have the interaction between one molecule, one atom of the liquid with all the other molecules or atoms of the liquid itself. And this, let's say, this terminology and this description is due to Landau. So the idea is, as long as it is possible to maintain a correspondence between single electron levels in the independent electron approximation to single electron levels in the interacting electrons approximation. So as long as you may suppose that the effect of the interaction is just a sort of perturbation of the independent electron picture, then this, let's say, single electron approximation is still valid. Someone calls this electron a quasi-electron because it's not actually just an electron, but is an electron interacting with all the other electrons. So in this picture, if, let's say, if you were able to turn on the interaction, at first the interaction you start of the independent electron system, and as you increase the interaction, you have always this one-to-one correspondence between this system and the other system. Then at this point, the single electron level is fine, even if the single level is not an actual electron, but is this quasi-electron. So in this case, if this correspondence is fine, we may keep this single electron picture. The single electron picture fails when this procedure may not be applied. And I just give you an anticipation of where this fails. If, for instance, you consider superconductivity. In the case of superconductors, you have the formation of couples of electrons. We will see that later. So due to the interaction between the electrons in the system, the actual system is described by couples of electrons, not by single electrons. At this point, if you have a system that is described in terms of couples of electrons and not of single electrons, that system cannot be obtained starting from the single electron picture just with a slight perturbation, because the configuration of the system is completely different. It's just like as if you would like to discuss, for instance, if you consider a molecule is something that is quite different from single atoms. So the molecule cannot be expressed as a perturbation of single atoms. The molecule, is not just a perturbation of the single atoms included in the molecule. So only in the case that this correspondence can be found, we may still use the single level approximation and single electron approximation, where electron means this quasi-electron state. So for all the system where this picture is fine, we may go on with this interpretation. So continue the discussion of the interaction in terms of single electron levels and just have a modification of the energy to include the effect of that interaction. And the system where we may use this approach are called normal Fermi systems. So the superconductor is not a normal Fermi system. But again, I wanted to introduce this part just here, just as a comment, a general comment to conclude the this topic. And if you do you have questions or comments concerning this topic in general, apart from this last point? So these last minutes, okay. In these last minutes, I would like just to introduce the new topic. And before going on, a question. What I would like to discuss now is the effect of lattice oscillations. Have you already seen in a bachelor course the effect of lattice oscillation in the one-dimensional chain? Sì, voi diciamo, a strutture so che avete fatto la catena di la catena di atomi che oscillano. Quello sì. So let's say, my idea is to make directly the three-dimensional case with the full calculation of that case. So I will not give anything for granted, and I will do the calculation from the beginning. So I just make this question to know whether you have an idea of where the one-dimensional calculation ends. So what are the conclusions of that? Because some of the conclusions of the three-dimensional case will be quite similar to the conclusions that we have in the one-dimensional chain. So if not all of you have already seen the one-dimensional chain, please let me know, and I will indicate where that calculation is found, just to have an idea of what is going to happen. So in the next lessons, I will discuss the effect of lattice oscillations and what is the motivation behind the fact that one tries to see what happens if the lattice, the ionic lattice, is not rigid, let's say, as I have supposed up to now, but may display oscillations. So what are the motivations behind the idea that some oscillations may be displayed by the ions? On one side, the ions are positive charged particles, and for the moment we have supposed that those particles occupy fixed position in space. So we are saying that the uncertainty over the position of the ion is zero, because we perfectly know what is the position of the ion. And in principle, this is not expected by a quantum mechanical particle, because in general, you expect that there is an uncertainty over the position of the particle due to the uncertainty principle. Then there are also other motivations behind that. For instance, you have seen the results of the Bragg experiment. The case of the Bragg experiment, you use electromagnetic waves in the X-ray band. You shine the system using those X-rays, and what you see is that for fixed values of the angle, you see a peak in the intensity of those X-rays coming out from the solid. So you see peaks once you have fixed the symmetry of the lattice, for instance, a cubic, FCC, BCC, whatever. Then you see some peaks corresponding to specific angles. And what is seen is that in general, the intensity of the peak has a temperature dependence. So as you change the temperature, the intensity of the peak decreases. So this means that something changes into the system due to the temperature, and those changes are due to the ions, because the Bragg peak is not due to electrons, but is due to the ions. So the idea that something may change in the system due to temperature is given by, for instance, the temperature dependence of the peak. Then if we go on discussing the lattice as a fixed system, we may not describe the melting process, because during the melting, the inter-ionic forces are no more able to keep the ions in their positions. So at some point, you have that the ions transform from a lattice into a liquid. So this transition cannot be explained if we suppose that the lattice is a strict, rigid structure that never changes according to temperature. Then there is there are also other physical motivations, because, for instance, if you consider insulators, if you just consider what I have told you up to now, in insulators, you have no net charge flow as you apply an external field. But as the electrons are the only particles that may transport energy and charge, if you have an insulator, in principle, you should expect no energy transmission within the solid. No energy transmission, this means that no heat may be transferred through an insulator, but this is not correct, since we have heat transmission by insulators. So, and another thing is that for the moment, we have discussed in the past weeks of collision with something, but we have not still been able to demonstrate what is this something. So maybe the configuration of the lattice may have an impact over the motion of the electrons. In fact, we have seen that just considering the contribution of the lattice to the wave function of the electron gives a huge contribution to the dynamics of the electron, because we have, let's say, all the things we said concerning block electrons, the velocity of the electrons, all the effects that we have observed due to the semi-classical model are effects that come from the use of the lattice into the as a possible contribution to the electron dynamics. So what we expect is that maybe the fact that we allow the lattice to oscillate may also give us some indication concerning the conductivity. So maybe this is helpful to explain why the resistivity changes according to temperature. So there are different motivations behind the fact that the lattice may not be purely static. So that the lattice may not just be there in the background, fixed and rigid, but may have may contribute to the dynamics of the electrons. And a strong indication about that is the lattice has a contribution on the dynamics of the electrons is given again by superconductivity, because what they saw is that the critical temperature of a superconductor depends. So if you consider a superconductor, the critical temperature depends on the isotopic composition. What does that mean? If you have a superconductor, for instance, niobium, and you replace the ions of the lattice using isotopes of the same element, then the chemistry of the system doesn't change, because the chemistry depends just on the number of protons that you have in the nucleus. But the mass of the ions that you have here changes, because the mass depends also on the number of neutrons. So if you change the isotope, you change the number of neutrons in the nucleus, and you leave the number of protons unchanged. The fact that the critical temperature depends on the isotopic composition is an indication of the fact that the critical temperature, that is something related to the electrons, because in a superconductor, we observe that below the critical temperature, the resistivity drops to 0. So that is a property that is due to electrons. So this property related to electrons is affected by a property that is specific for ions, that is the mass of the ions. So if you change the mass of the ions, then you change the property of the electrons. So this is an indication of the fact that electrons and ions are strongly connected, not just by charge, because if you change the isotope, the charge is always the same. So it's not just chemistry, it's something more deep that is related to the mass of the ion. And the mass of the ion may be important, for instance, if you consider an oscillation, because you have that the mass that is oscillating changes its value. So many different points brings us the suggestion that maybe the effect of the ion oscillation may be important for the electron dynamics. And yeah, so from let's say now it's nearly 11:30, so I will not start with any calculation. So from the next lesson, what I will try to do is to, let's say, use as a starting point the Bravais lattice of the system and allow each of the ions of the Bravais lattice to display a displacement. So what we will do in the next lessons is to see what happens if the position of all the ions is allowed to change with respect to the equilibrium position that is represented by the Bravais lattice. And in this case, we will do the calculation just for the three-dimensional system. So for the system where we have a three-dimensional lattice, and we'll let the ions move with respect to the equilibrium position. And so what we will try to see is what is the impact of that on the electron dynamics, and I'm sorry for that. I was missing an important point that I forgot to mention. Another thing that we have not been able to discuss and to explain is the dependence of the specific heat on temperature. So we know that the experimental result is given by a dependence like this one here. So the specific heat has a saturation value at high temperature, but then at low temperature, we have a power law dependence that is represented by a T to the power of 3 low here. But for the moment, the only contribution to the specific heat is given by electrons, and the electrons have a linear dependence over temperature. So, and we also saw that the this contribution is way lower with respect to the actual contribution that we should expect to have in the system. So for the moment, this dependence is completely unexplained. What we may imagine is that if we let the ions to oscillate in the system, we have an additional system that may contribute to the total energy of the solid. Because if we have a system of oscillating masses, this system of oscillating masses has an energy. So the fact that we may have an additional source of energy of the system is an indication of the fact that if possibly that energy may change with the temperature, then that energy may contribute to the specific heat, because the specific heat is 1 divided by the volume, the derivative with respect to temperature of the total energy. So if this term here has a new contribution, in this case the ionic one, then maybe we are able to justify, we have the opportunity to justify this dependence. So we will start from here. In the next lesson, I will try to see what is the effect of the oscillations of the ions. Okay, so now I stop here, stop the registration, and so the next lesson will be on next Monday, and the lesson of tomorrow is shifted to December 11 at 9 a.m., not p.m.